Hello everyone, welcome to this next video on classical mechanics. In this video we shall see all about Hamiltonian. We have already studied what a Hamiltonian operator is, how we can derive the equations of motion in using these approaches. Well, in this video let us see what is the advantage and what is the significance of using this approach. So first of all, let us see what does this Hamiltonian operator defined using the equation summation qj dot pj minus l, right, where j varies from 1 to n. So this operator, what does this signify? So as we have discussed this in the previous video, that in some cases this h that denotes the total energy of the system. So basically the dimension of this Hamiltonian H and the dimensions of Lagrangian operator L, right, they are same as that of dimensions of energy. So this is one point to note. Another point is that this H represents total energy when our system is conservative, one condition. That means the potential does not depend upon the generalized velocities q dot, right? So please note that what is conservative system, where the potential energy does not depend upon the generalized velocity. So this when you take the partial derivative of this potential, so potential basically is a function of qj only, so that would come out to be 0. So for conservative system we have this thing that Hamiltonian represents the total energy of the system. Moreover, when we apply the coordinate transformation, that transformation is time independent. That means this quantity is equivalent to 2t. So what does this represent? So our Hamiltonian equation was summation over j pj qj minus l. So basically when our coordinate transformation is time independent, so this quantity becomes equivalent to 2 times of that of kinetic energy. So this is 2t, and what is L? L we know it is T minus V. So the difference of kinetic energy and the potential energy. So let us substitute this over here. So from here we get that H represents the total energy of the system. That means the sum of kinetic energy and the potential energy, provided we have the conditions that the system is conservative and the coordinate transformation is time independent. In another case, this h represents the constant of motion. This quantity h is equal to summation varying over j pj qj dot minus l, that was constant, and it was constant when we have this condition that the coordinate transformation, these equations involve time explicitly, right? So this is the condition for h to be constant of motion. But usually when we are solving the real life systems, in that the Hamiltonian which is both the constant of motion as well as the total energy is required, right? And we are looking for those systems for which these two conditions they are true, right? So this is one thing. Another thing is that Hamiltonian do not require the individual calculation of force components as we saw in the Lagrangian. So the Hamiltonian approach goes well with that of Lagrangian approach. So basically we are building on to Hamiltonian approach using the Lagrangian approach, right, where we have eliminated the use of all forces and vector quantities. So here this is also a scalar quantity, just like that of Lagrangian. But the thing that differentiates it from Lagrangian is that this Hamiltonian, being a scalar, it provides a method which could determine the total energy of the system. Although in some few particular cases we are saying this thing to be true, but it provides us or gives us a method to calculate this total energy of the system. So in the last video I have told you that calculating the equations of motion using the Hamilton's equations canonical equations or from the Lagrangian equations. They are quite a lengthier process as compared to that of calculating them from Newton's equation. So why do we do so when we have simpler methods to calculate these equations of motion for the simpler cases? This is why, because for the simpler cases, what we have, we can learn such approaches, some processes, how they are working and how we can solve different problems into using these approaches, right? So once we learn the technique of solving these approaches, we can do more abstract kind of thing, right? For example, the first reason that I have stated over here is that this Hamilton's method that gives the starting point for many other formulations, the abstract formulations of mechanics. Why? Because here we have a freedom to choose whatever coordinates and the momentas that are required to completely describe the system. So basically we can talk about abstract things which are not based just upon the displacements and the simple velocities that we talk about. We can have more other things also. So this approach based upon coordinates and momenta, where we are keeping these two things on equal footing, so it forms a base for other abstract formulations. The next reason is that in the study of energy changes in atoms and molecules, there the forces cannot be directly calculated. Moreover, the force of constraints, they become meaningless when we talk about such small atoms and molecules. So there, in order to study the energy changes, we take use of these approaches, the Hamiltonian approaches, where this Hamiltonian, the numerical value of this Hamiltonian represents the energy of the system, right? So that is why we use this approach. Let us see third reason. It provides a convenient basis consisting of the generalized coordinates and momenta, the corresponding momenta, for the development of other detailed subjects like quantum mechanics and statistical mechanics, right? Moreover, using this technique, although nothing new has been added to the existing mechanics, but another approach to handle such systems has been developed in this subject. Moreover, as we have talked about atoms and molecules, for microscopic systems, this Hamiltonian dynamics enjoys wide application. So it has a huge application when you wanted to see some good applications of either from this quantum side in atoms or molecules, or from the statistical mechanics. There you can formulate abstractly different problems and solve them. So there, this technique of Lagrangian and Hamiltonian comes out to be really handy. So I hope I convinced you for using this Hamiltonian approach. Well, that is it for this video. I'll see you in the next video.